morning, my dear students. In this session, the continuation of electromagnetic induction is Good morning, my dear students. Today, in this session, the continuation of electromagnetic induction chapter we are doing. So the name of the topic is Lenz law and conservation of energy. And this is the Lenz law is used to find the direction of induced current. To find the direction of induced current. Look at here. To find the direction of induced current where? In this straight wire, there can be a production of induced current. In the circular coil also, there can be a production of induced current. Question is, where the direction of induced current is found by using Lenz law. So this is in a circular coil. Not only in a circular coil, in a coil. In a coil, right? In a straight wire, the direction of induced current can be found by using Fleming's right hand rule. So that's what I'm going to use, right? Fleming's right hand rule is used to find the direction of induced current in a straight wire. Alright. Now the topic is Lenz law. So Fleming's right hand rule is not our topic, and that will be discussed at the end of the chapter. Mostly after this Lenz law. What is Lenz law? Why it is used? I have told you. What is Lenz law? We have not yet started. Right? Why the Lenz law? We have started. And I have written one more term here, conservation of energy. You know about the conservation of energy. Energy neither be created nor be destroyed. It just takes from one form to another form. That's called the conservation of energy. My dear students, how that conservation of energy is connected with this Lenz law, that's the most important part and the beautiful part of the topic called Lenz law. Come to the topic, come to the definition of the Lenz law. Most of the students will get confused by reading the definition itself. The direction of induced current create an induced magnetic field. Okay, stop till here. Okay, direction of induced current create an induced magnetic field. So that we know. Wherever there is a current passing through a coil, that may be current passing through a wire, the magnetic field will be produced around it. So if the current is producing magnetic field, so this is what the current through the original battery, not through the magnetic flux change. Okay. So whenever there is a current passing through a coil or a wire, there is a magnetic field associated with it. For example, if this current is induced current, and definitely the induced current will produce a magnetic field, so that is called induced magnetic field. And when this induced concept will come, when there is a electromagnetic induction phenomenon is taken place. All right. Now I am going to draw a simple simple flow chart for you to understand the Lenz law in detail. Okay, listen. Wherever there is a magnetic flux change that may be increasing in the flux or decrease in the flux associated with a coil. Right? So many times we have discussed. So there is a coil, you imagine here. A magnet is moving towards the coil. The flux associated with the coil will be increases, yes or no? The number of field lines passing through the coil will be keep on increases when it is moving towards it. When the same magnet is moving away from the coil, the flux linked with this coil will be decreases. Whatever it may be, there is a magnetic flux change. Because of this magnetic flux change, what happens? Induced EMF is generated, yes or no? Induced EMF means what? The virtual polarities of the battery, the temporary polarities of the battery is formed. So when polarities are formed, positive terminal and negative terminal you have, so then definitely the current will be moving, right, in the coil. So induced EMF will produce induced current, and this induced current will not simply be quiet. It will produce induced magnetic field. Alright, my dear students, induced current will produce induced magnetic field. This is what the part what we have studied just now. The direction of induced current create an induced magnetic field. So induced current is produced induced magnetic field. Now let's read further. That opposes. That means what? That means the direction of induced current. The direction of induced current will produce induced magnetic field. Induced magnetic field also will have some direction, right? Induced current will have some direction. This you can find by using Lenz law. That is what I told you here. Lenz law is used to find the direction of induced current in a coil. Okay, and induced magnetic field also will have a direction or polarity. Direction or polarity. North pole, south pole. Okay. Now, the direction of induced current create an induced magnetic field that means the direction of induced current opposes. This is the most important word in this definition. So this opposes the cause that produces it. This induced magnetic field polarity or direction always opposes the cause that produces it. Opposes the cause that produces it. What is the cause is for the production of magnetic field? Can I say this cause is a magnetic flux change? Tell me. Can I say this cause is the magnetic flux change? Yes, the cause for the production of induced current or for the production of induced magnetic field is the magnetic flux change. Alright. So this magnetic flux change will always oppose, see here, this induced magnetic field or induced current will always oppose the magnetic flux change. If the flux change linked with the coil is increases, then this induced magnetic field will try to decrease the magnetic flux change. For example, look at here, my dear students, a simple example I am going to take here. See, there is a coil here. North pole is kept here. North pole of a magnet is moving towards the coil. So flux change will increase, right? Because more number of field lines will pass through the coil as it is moving towards it. Okay. As the magnet is moving towards it, the number of field lines linked with the coil will increase. So because of the flux change, induced current will produce in the coil and induced magnetic field will produce in the coil, and that magnetic field, that magnetic field will try to reduce the magnetic flux linked with the coil. Okay. So if we start understanding with the examples and illustrations, you will understand it better. But remember, this is the flowchart. Magnetic flux change will produce induced EMF that produce induced current. that produce induced magnetic field. That induced magnetic field will always opposes the cause that produces it, opposes the magnetic flux change. Alright, let's see the example. Simple. There is a coil. See, there is a battery connected to it. I am not writing it. But there is a battery connected. It must be a closed circuit. So this north pole of a bar magnet moving towards the coil. What happens? More field lines are passing through the coil. Magnetic flux is linked with it. Listen. When the magnetic flux is linked with it, see, magnetic flux change is there. More field lines are passing through the coil. Induced EMF will produce, induced current will produce. How the induced current will produce here, that is important. For time being, forget about the direction. Induced current is produced. Induced magnetic field also produced. This is important now. A magnet is moving towards the coil. Magnetic flux change. More field lines are passing through it. Induced current, induced magnetic field. Now this induced magnetic field will try to decrease the magnetic flux. See here. Magnetic field lines are moving in this way. More number of magnetic field lines are moving through the coil. More number of magnetic field lines are moving through the coil. In this way. In this way. The induced magnetic field will produce the magnetic field lines in the opposite way. That is called the opposing. Understand? So induced magnetic field, this coil will produce induced magnetic field that produce the magnetic field lines in the opposite way of magnetic field lines of the magnet. So that what happens, the net magnetic flux will be decreases. Okay, this induced magnetic field will always try to oppose the magnetic field strength of this magnet. When more field lines are associated with a coil, this induced magnetic field will try to decrease the magnetic flux. When magnet is moving away, what happens? Look at here. When the magnet is moving away, look at here. I'll draw here. This is the coil, magnet. It's north pole and south pole. When the magnet is moving away, the number of field lines passing through is very less. Number of field lines passing through the coil is very less because it is moving away. In this case, what happened? The induced magnetic field will try to increase the flux. Here, induced magnetic field will try to decrease the flux. Okay, clear? Let's see. Magnetic field lines are moving in this way by increasing the flux change. To decrease this flux, this induced magnetic field must produce field lines in the opposite direction, right? So, if you want the field lines in the opposite direction, okay, you know, a current carrying circular coil will behave as a north pole or a south pole. The face of the coil, it's called the clock face rule. According to the clock face rule, what is that? According to the clock face rule, if the current is moving in anti-clockwise direction, so this face of the coil will behave as a north pole of a magnet. If the direction of current is clockwise, this face of the coil behaves as a south pole. Remember, this is anti-clockwise and this is clockwise. Okay, clear? This is called the clock face rule. Now, so come back here. So this is we are looking from here. We are looking from the magnet end. So this way, this is the magnet. We are holding the magnet and we are looking from the magnet end. So when the magnet north pole is moving towards here, more field lines will be passing through the coil. Induced magnetic field will opposes the magnetic field of this. Opposes means induced magnetic field will produce a field lines in this direction. Okay, field lines in this direction. So in this direction field lines are moving means this particular phase must be a north pole, yes or no? this particular phase must be a north pole. Then only from the north pole magnetic field lines will originate. Yes or no? Clear? So magnetic flux change is in this direction, right? Magnetic field lines passing through the coil in this direction, and the flux change is more. The induced magnetic field will try to decrease the flux. So decrease the flux by keeping the magnetic field lines in the opposite direction. So magnetic field lines must move in this direction through the coil. That means there must be a north pole is developed here. Then because of this north pole, because of this induced magnetic field lines are in this direction, and anyhow the magnet is moving in this direction, right? So magnetic field lines are in this direction, and due to induced magnetic field lines are in opposite direction. So finally our concept is done, right? So what happens? So it must be a north pole. That means the current, induced current must be in anti-clockwise direction. Then only there is a north pole will be developed here. Magnetic flux change. Yes, due to the movement of the magnet, there is a magnetic flux change. Induced EMF. Because of the magnetic flux change, induced EMF is produced. Because of induced EMF, induced current is produced. Yes, induced current direction is anti-clockwise we found. And induced current will produce induced magnetic field. Yes, see the north polarity of the pole. And that opposes the cause that produces it. Yes. By forming a north pole here at a particular phase of the coil, there is an opposition of the magnetic flux change. That is the Lenz law. See this? Here the magnet is moving away, but the field lines are entering only. Magnet is moving away. Here the interesting part. When the magnet is moving away, there is a magnetic field produced here because of the flux change. But that magnetic field will try to increase the flux. Here, decreasing the flux. The induced magnetic field is trying to decrease the flux. I am writing here, in this case, induced magnetic field will try to decrease the flux. Here, induced magnetic field will try to increase the flux. Okay, increase the flux. So when it is moving away, the magnetic flux is decreases, and this induced magnetic field will try to increase the flux. So here you can see, this is the coil. Magnet is north pole here, magnet north pole is moving away. So some magnetic field lines are passing through the coil in this direction. So how the flux linked with the coil will be increases? By creating the magnetic field in which the field lines are also moving in the same direction of this magnetic field lines. Understand? So because of the flux change, again I am telling you, because of the flux change, there is an induced magnetic field associated with the coil. Okay. Now what happens? That coil will produce magnetic field, and that magnetic field will try to increase the flux by sending the magnetic field in the same direction of the flux, same direction of the initial magnetic field lines. So in the same direction you need magnetic field lines, means this particular phase need to be south pole. Understand? Because field lines are already in this direction. In the same direction you need magnetic field lines, means it means the south, it must be a south pole, because magnetic field lines start from north pole and moves to the south pole and pass through the south pole also. That doesn't matter to us. So magnetic field lines reaching the south pole. So then only the magnetic field lines and the magnetic field lines of this bar magnet will be in the same direction with respect to the coil. So there must be south pole will be developed here. South pole means the current direction is clockwise. Right? So this is anti-clockwise direction and this is clockwise direction of induced current. Clear? Here also the same thing is possible. You can see there is a magnetic flux change. Because of that induced EMF, because of that induced current, and because induced magnetic field, and this induced magnetic field is opposing the magnetic flux change. Yes, this induced magnetic field only is trying to increase the flux. When there is a flux linked with this is decreases, and induced magnetic field will increase the flux. When the flux linked with the coil is more, the induced magnetic field will try to decrease it. So that's called the Lenz law. According to the Lenz law, we have found, and we could found the direction of induced current is anti-clockwise when we are looking from here. This is our eye. When we are looking from here with respect to the magnet, so south pole is found here. Now the interesting thing I'll tell you, listen. Simple way. When a north pole is moving towards the coil, north pole will develop. Simple. When a north pole is moving towards the coil, north pole will develop. Opposite. Okay. When a north pole is moving away from the coil, south pole will be developed here. Opposite, right? It is moving away, right? Here. North pole is moving towards the coil. According to the Lenz law, north pole will form. Right? Repulse. Here. When north pole is moving away, so there is a south pole is formed. Alright? Exactly, my dear students. Here, carefully see, here I am drawing here. This is the coil. South pole and north pole. Now the south pole is moving towards the coil, and there is a south pole is developed here, and this is the coil. And if you see south pole and north pole, when south pole is moving away from the coil, and definitely there will be a north pole is formed. Okay, so direction of the induced current is clockwise here. So direction of induced current is anti-clockwise here. So my dear students, you practice this. You just practice this, then the Lenz law you will understand very well, right? So the commonly asked questions are also there in the Lenz law cases. Okay, so now we'll be discussing, there are several cases in the Lenz law which are very important for your NEET exam, that we'll discuss now. Alright, my dear students, let's discuss some applications of Lenz law. Few applications of Lenz law. Clear? What we had discussed already, imagine there is a coil. The south pole is moving towards the coil, and definitely there is a south pole will be produced here. So then only the Lenz law is valid. Then only the correct identification of induced current in the coil. Now this is what the direction of the current is clockwise. So the direction of induced current is clockwise. So there is an induced current production in this case. Yes or no? There is an induced current production in this case. In the same case, let's discuss one more. So this is the coil. Now the magnet which is having north pole and south pole in this way is moving away from it. So do not simply write this is south and there will be a north pole developed here. No, this is the case already we have discussed in the last slide. Here there is a south pole will be formed. Understand? You can refer the previous slide. You will apply Lenz law here and here also. So then the perfection will come in applying the Lenz law. Here also the direction of the current is clockwise and induced current is produced in the coil. Because in both the cases there is a magnetic flux change. Yes or no? In both the cases there is a magnetic flux change, my dear students. Let's take the concept or the case. There is a coil. Close to this coil, a magnet is placed which is having north and south pole, and about this axis the magnet is just rotating. That's it. We are not changing the position of the magnet. Imagine if this is the coil, this is the magnet. See, the magnet is just rotating in this way by keeping it the same position. Is there any magnetic flux linked with this? Definitely there won't be any magnetic flux change. There is a magnetic flux linked with this. Magnetic flux change will not be linked with this. Okay, clear? Because constant magnetic field lines only will be passing through it. Whether you rotate it or not, keep it the magnet here. There are some constant magnetic field lines will pass through it. So there is no magnetic flux change. Due to that, no EMI, no induced current, no EMF. So I can say the induced current will not be produced in this case. This is one application. Let's see the another application, dear students. Three main important applications are there. Three main, right? Number two, the second application is, so there is a coil. A circular coil is placed in this way. This is the circular coil I have. A magnet, this is the north pole, right? A magnet is dropped, a freely falling magnet, you can say. A magnet is dropped here. North pole is here. So when we are observing from the magnet side, so this is the magnet, I am observing from here, from the up, see, you can say I am observing from here. Magnet is moving towards the coil. North pole is moving towards the coil. So definitely north pole will be developed. North pole means anti-clockwise, yes or no? It's a no. When there is a magnet whose north pole is here moving towards the coil, what happens? The direction here, the direction of the current, let's say in this case, anti-clockwise is the direction of induced current. Because of this anti-clockwise, this particular phase, when I am looking from here, this is what my eye, when I am looking from here, this particular phase of the coil behaves as a north pole, and we know this north pole and north pole will repel. Understand? Now the question is, look at here carefully. This will be moving with some net acceleration, right? So in this case, we are going to find the relation between acceleration of the magnet and acceleration due to gravity, because it is freely falling. Okay. Most of the time this question was asked in JEE, NEET, CET, and even for the board exams here. Look at it. Here north pole is developed, so there is free body diagram. Let me draw free body diagram of this. mg will be moving downwards, right? So if you take, this is the magnet here, north pole, and its mg will be here. On the magnet, the repulsion force of this magnetic field, repulsion force of this induced magnet, see, north pole is here, and this pole or this particular coil phase becomes north, and north repels, and this is the repulsion force. But the moment of the magnet is mg only, towards mg only, so that is why net force will be mg minus capital F is equal to the net force of the magnet. So this mg minus force, which is the repulsion force, I can say the repulsion force, which is equal to F net, I can say it is ma, which is mass of the magnet into acceleration. We know force is equal to mass into acceleration. That force is net force. Net force is mass into acceleration. Our aim is to find what? The relation between acceleration of the magnet and g, acceleration due to gravity. So this m, let this m divide this left hand side part, so it will be g minus repulsion force by m, which is equal to a. If you carefully see here, my dear students, what happens? A is equal to g minus something. Imagine, for example, if g value is 10 meter per second square, and what is the a value? 10 minus something. So definitely it is less than 10. Yes or no? Definitely it is less than 10. Alright. A is equal to 10 minus something. G is 10, A is 10 minus something, it is less than 10. So always your A value will be lesser than the G value. That's a relation. When a bar magnet is dropped through a coil, what happens? Its acceleration always will be less than G. This is what the proof for this. For example, this you can find out now. Imagine the magnet is passed through the coil. So now, after passing through the coil, what happens? This is your north pole. So this is your south pole. So now the south pole is moving away from the coil. See the condition. Here south pole is moving towards the coil. When south pole is moving away from the coil, what happens? South pole is moving towards the coil, south pole is formed. South pole is moving away from the coil, north pole will be formed. When we are looking from the bottom. This is the coil. Now the north pole is crossed the coil and like this, right? See, when we are observing here, I am talking about this. Always our observation point must be as per the magnet, with respect to the magnet. So this is the magnet. With respect to the magnet, I am observing in this direction. So when we look from here, so what happens? South pole is moving towards. So south pole is moving away from the coil. This is the coil. South pole is moving away from the coil, and the other side north pole will be formed. North pole means again anti-clockwise direction. Understand? So here mg, if you take the free body diagram of the second case, mg will be downwards minus south, and north pole is formed for the coil, right? This is south. So both will be attracted. So this is called attraction force. And mg is downwards, and this south pole and the north pole of the coil attracts minus Fa, that is what attraction force, which is equal to m into A. The net same way, same like that. So here also G minus attraction force by m is equal to A. Here also A is less than G. So when the magnet is before passing through the coil and after passing through the coil, wherever may be the situation, take a ring, drop a magnet, any place, its acceleration will be less than G only. Remember, my dear students. Imagine this coil is cut. Imagine the coil is cut. When the coil is not filled in the sense it's not complete. The circuit is not completed. There is a magnetic flux change, but there is no induced current. There is no induced EMF because it is not fixed. It is not complete. If the coil is cut, no induced EMF, no induced current. Because in the closed circuit only these things will happen. Okay? Clear? Now, third application is the most important application. In third application, 3 cases are there. Only 3 cases. There is a coil. There is a wire. Here there is a coil, and close to it there is a straight wire. Here there is a coil, close to it there is a straight wire is kept. In this straight wire, no current is passing. When no current is passing, there is no magnetic field associated with this. Yes or no? According to the right hand thumb rule, if you see this straight wire and the coil is placed in the same plane, what happens? So because of this current, there are some field lines will be present in this coil. See, according to right hand thumb rule, right side of this, if the current is passing, for example, in this case current I is passing, what happens? Right side of this, the magnetic field lines are into the plane. Left side of this, the magnetic field lines are out of the plane. Understand? Come back to this. When there is no current, no magnetic field, no induced magnetic field, all those things. So for example, if the current is constant, what happens? If the current is constant, so right side of this, the field lines are into the plane, and left side of this, the field lines are out of the plane, my dear students.
field lines are out of the plane. So the magnetic field lines passing through the coil is constant because the current is constant. Okay. Because the current is constant, field lines are constant. In the constant magnetic field, this coil is kept. So there is no magnetic flux change. Magnetic flux is linked with the coil. That's it. Magnetic flux change is not there because our electromagnetic induction topic is completely based on magnetic flux change, not on magnetic flux. This is the statement I am giving you from the last session. Now, forget about this. So in this case, what happened? No induced EMF or no induced current. Leave it. Come back to here. The most important two cases. When the current is increasing, so what I am doing here, the current is keep on increases. When the current is increases, the field lines coming out of this coil increases because of the direction you see. Understand? So current is increasing means whatever it may be, according to the right hand thumb rule, right side of the current carrying wire, the field lines are into the plane. Left side of the current carrying wire, field lines are out of the plane. Field lines are out of the plane here. But as I am increasing the current passing through the wire, so the left hand side, the magnetic field lines also will increase. So that means magnetic flux will increase. Left side, magnetic flux will increase. When there is a magnetic flux change, we discussed already, when there is a magnetic flux change and there is a induced current and induced EMF, that will produce magnetic field, induced magnetic field. Understand? Induced magnetic field will oppose the cause that produces it. These are all you know, right? See, when we are increasing the current, magnetic field lines passing through this also will increase and their direction is out of the plane. Okay. So there is induced EMF, induced current, induced magnetic field, and that induced magnetic field will oppose the original magnetic field. So original magnetic field lines here, they are increasing. So induced magnetic field will try to decrease the magnetic field strength by producing the magnetic field in the opposite direction. Here the magnetic field is in this direction. So this wire will produce a magnetic field in the opposite direction. Opposite direction means the other side. So this side original magnetic field lines. Now opposite side. See, by using right hand thumb rule once again. See, opposite of the right hand thumb rule. I told you in the circular coil magnetic field due to a circular coil we discussed already. This way. Clear? So now, alright. In this way only current need to be produced, then only the field lines will be in this direction. So which pole it is? Clockwise direction. Clockwise direction, there is a south pole. Understand? So in this case, induced current is in clockwise direction. Here, current value is decreasing. Carefully see, my dear students, current value is decreasing, but the magnetic field lines will never change. Current value is decreasing even though the right side of this wire, the field lines are into the plane. Left side of this wire, the field lines are out of the plane, my dear students. Left side of this magnetic field lines are out of the plane. Out of the plane. But here, current is decreasing. Magnetic field lines are also decreasing. Magnetic flux linked with the coil decreases. An induced magnetic field will try to increase the flux by producing the magnetic field lines in the same direction of the magnetic field, original magnetic field. So now, in the same direction, this coil should produce magnetic field means, look at here, this way, out of the plane, right? In this way, it will produce magnetic field. So this must be the direction of induced current. See, according to the right hand thumb rule, opposite to the right hand thumb rule. See here, so this is how the direction of the current. So then definitely this must be the anti-clockwise. So that indicates north pole will be developed here. So this is called induced current direction will be anti-clockwise. Understand? So like these questions will be asked. In which direction induced current will develop? What pole develops over there? So in this way, questions will be asked, my dear students. And let's discuss a little more concepts of law of conservation of energy in the next class. Thank you so much. All the very best for your assignment.